Hello, we are the Coding Colonials, and this is our prototype design wall. This is our first model of the initial stage of the first responder device. You can see that the logic is very complex, and that the heart rate receiver is not even fritzed into the sketch. We then move on to our second iteration. Here, we simplified our Boolean logic, and we still have to fix the problem of the heart rate monitor missing. You can see that the data transmission wires are now added so that the Boolean logic is now simplified. This is a common technique used in electrical engineering. This is our third iteration. We noticed that after we took some voltage counts of everything, we needed to add a pull-up resistor so that we pull the voltage up. And we also simplified the logic to the simplest possible Boolean logic. And over here, we added the GSM shield onto the Arduino. And we got a fritzing model for the actual heart rate receiver. And with that, we came up with our final design. This is the schematic for our final design. As you can see, the Adafruit flora in the Arduino are here, and that there are two resistors located here.
This is a temperature component of our first responder device. It consists of a GSM shield, a resistor, the Arduino, and a temperature module. In our first model, our Boolean logic was too complex and there were way too many connections, which caused it to be difficult to solder. In our second model, we simplified our logic. However, at the RS socket, there was no voltage, and this caused no data to be transmitted. In our third model, we did some resistance calculations and voltage calculations, and we realized that we needed resistors at pin 2. And as you can see, we also lower the complexity. And here in the final model, we added the pull-up resistors needed, and we completely simplified our Boolean logic. Location of the person in need of medical assistance. Our first responder device uses multiple algorithms and the GSM shield. The GSM shield will send the longitude and latitude of the person in distress, and it will store the latitude as norm in the variable x, and the longitude as norm in the variable y, and then it will calculate the distance using the distance formula. Then, using Dijkstra's algorithm, we can calculate the shortest way between any two nodes. After calculating the shortest path between the drone and the person in need of medical assistance, we can send this information to the drone, which will fly to its necessary place.
The first blueprint for the first responder drone. As you can see here, there are 6 rotors, which are hard to manage in tight spaces. Here is an underneath view with 2 ultrasonic sensors, which can help with landing and takeoff. Here is the second blueprint. This design was bad because the ultrasonic sensors on the bottom were affected by the weight it could be carrying, such as painkillers or inhalers. As you can see here, we also added the 4 rotors. Here's the third blueprint. We added a little bit more space to carry basic medical equipment. And there's also 4 rotors, and the ultrasonic sensors were moved up so it wouldn't take much space. However, this idea was bad because there was no way for the paramedics to monitor the person in need of medical assistance. Here is our final blueprint. As you can see here, there's the 4 rotors, the 2 ultrasonic sensors, space to carry basic medical equipment, and the camera, which uses TCP stream to connect with the paramedics so they have an idea of what they need to be expecting. This was a good idea since it allowed full visibility to the person who was in need of assistance and can take off easily due to the good ultrasonic sensors and good placement. It also allows good carrying capacity of the basic medical equipment.
This is the physics component of the drone. This was our initial equation that we came up with, where P represented power in watts, and this assumed 100% efficiency, and little p represented air density, A represented area of the rotor, M represented the mass of the drone plus payload, and G is a local gravitational force. The vectors that we comprised included magnitude and direction like any other vectors. So these were our 4 vectors: G little p, M little p, G A, and M A. The formula here gets us the power that we need to fully optimize and power our drone. The formula is P equals square root of the quantity of the absolute value of 1 over 4 square root of PA times 2mg to the power of 3 over 2 absolute value, close absolute value, squared. So, this may seem like a very complicated and irrelevant formula to our project, but the relevance in it is that we derived this formula through helicopter data modeling, and we plugged in some MATLAB code for these 4 vectors, and we derived this formula, and it accurately gave us the power. This allows us to correctly and precisely compute the power. These values here, such as these constant values, such as 4, 2, and 3 over 2, are rounded off. And then we put them through regression analysis, and we got this formula. And we noticed that we were missing the vector for wind speed. And we wanted to fix this. So we also iterated through and came up with a new formula. As you can see now, we now have 6 vectors instead of just 4. And this allows us to be so precise that when computing our drone's power, and when we checked it with a multimeter, we were 0.000001% off, which is about the closest approximation we have ever got. So the formula is the quantity square root of PA divided by 4 times 2mg, and we're taking the 3 over 2 power of that quantity, and we're multiplying that with 2 times PA plus 2L, and we're whole dividing it by 4L and 2PA. We're whole dividing by this, and we're creating a removable discontinuity in this physical, because in the case that there's such a accuracy that there are no area of the rotors, that we get an undefined value for this answer.